Hello, everyone. Good morning, good afternoon. My name is Carmen Guguta. I'm your host from Technobis Crystallization Systems. Today, we have with us Dr. Blair Bretman from Georgia Tech. But before I introduce our presenter today, I would like to welcome you to our webinar on polymer solubility and precipitation kinetics with the Crystal16, and tell you that this webinar is being recorded and will be made available tomorrow or in the coming few days. You will receive an email with a link where you can watch the recording or download the slides that are presented today. If you have questions, please make use of the chat question function of this platform or write to us at info@crystallizationsystems.com or contact directly Blair. It will last about 30 to 45 minutes. Questions we will take at the end. I will read them to Blair and we will do our best to answer to you. Before we really start, I would like to introduce to you Technobis. Who are we, for those that do not know our company? Although looking at the names, I've just had a glimpse of the names that the attendees today, so I recognize many of our customers. So I think you are already familiar with our Crystal16 and Crystal9 at least instruments. Technobis is a Dutch company located in the north of the Netherlands. We are a world-leading technology provider for solid-state research, process development, and formulation. Since more than a year ago, almost 2 years, we are also active in process chemistry, synthetic chemistry. We have 4 products in our portfolios. In the crystallization portfolio, Crystal16, here in the middle, Crystal9, or maybe a laser point. So the Crystal16, Crystal9, and the Crystal breather, and the reactor for reaction screening. The Crystal16, you might already know it, as I mentioned, is your instrument for solubility, for metastable zone with any type of solid state screening. And today you will hear from Blair about how you can use the Crystal16 also for polymer applications. Crystal9 with the camera technology work exactly like a microscope. Help you to actually visualize your particle, determine particle size, shape, D10, D50, D90. If you have a Raman spectrometer in your lab, you can connect it to the Crystal9, and as you would follow polymorphic transformations, for example, or chemical reactions in a normal case with the Raman, you would be able to do that also with the Crystal9. And the Crystal breather is the instrument for single crystal growth. It's really specifically designed to address that part of crystallization with specifically designed vials that mimic the NMR tubes where the crystallographer used to grow single crystals. It comes with a lot of gadgets, as I call them, evaporation, vapor diffusion, really to help crystallization. With this, I go further, and I would like to introduce to you our speaker today, Dr. Blair Bretman, Associate Professor in Chemical and Biomolecular Engineering at Georgia Tech. She received her Bachelor in Chemical Engineering at the University of Texas in Austin, and her PhD also in chemical engineering from MIT. Following her PhD, she was a senior research engineer at Saint-Gobain and a postdoctoral researcher in the Institute for Molecular Engineering at the University of Chicago. She was the recipient of NSF Career Award in 2021. In 2020, the ACS PMS Young Investigator Award she received, and in 2019, UPAC Young Observer Award. Her research focuses on linking molecular to micron scale phenomena to processing and multi-component complex mixtures to enable rapid and science-driven formulation and product development. Blair, thank you very much for being here today and sharing some of your latest findings from your group today with us.
Yes, thank you very much for having me. I'm excited to come and talk to you. I'm going to have my talk have a little bit of basics on polymers because I know a lot of the customers in the community associated is from the pharma industry. My PhD was actually related to pharmaceutical manufacturing, so I started in that area and moved into polymers as I grew my career. So I'm going to talk first about polymer solubility basics, how polymers work in solution, some of the theory that will help you understand the phase diagrams and the use of it with the Crystal16. And then at the end of the talk, time permitting, I'll talk more about polymer precipitation and how we can use a Crystal16 to understand polymer precipitation, which is one of the phenomena that's poorly understood within the polymer industry. So very basic, what are polymers? In the beginning of the 19th century, chemists started making these big macromolecules, but they didn't actually think they were large molecules. They thought they were small molecules that are associating with some sort of mysterious non-covalent bonds. So I think about this as having, paper clips sitting around and you've got some magnetization that associates them together. In 1920, Staudinger proposed what's called the macromolecular hypothesis, that polymers are actually molecules made of covalently bound elementary units called monomers. So this is if you think about making a chain of all your paper clips attached together. So this is a very fundamentally different way of thinking about it. And throughout this introduction, I'll share some of the implications of having these very large molecules. So how are polymers different from other material classes? So one of the ways they're different from a lot of materials is that they're very limited in the types of chemistry and the atoms that go into them. This is often things like carbon, hydrogen, oxygen, nitrogen, sulfur, and fluorine. So there's not a lot of chemical diversity when it comes to the actual atoms, although they can be packaged in lots of different ways. One of the biggest features of polymers compared to other materials is that polymer molecules themselves are very, very long. Like a single molecule can even be centimeters long. And so this leads to phenomena like chain entanglement. It leads to slow timescales of motion. They can be very dynamic in how they change, and their size will depend on the environmental conditions, which is part of what I'm going to talk about when I lead into solubility. Another important feature of polymers is that they're not fully crystalline. So unlike small molecule organics or small molecules where you have fully crystalline materials, polymers are always semi-crystalline or fully amorphous. They are never 100% crystalline. This has to do with them being this very, very large molecule that's very hard to pack into an ordered structure completely. And then finally, because they have so many linked monomers or linked functional groups, there's a lot of their behaviors driven by intermolecular forces. So this is due to the chemistry that they have, lots of hydrogen bonding groups or electrostatic groups, but also due to their large size and just a large quantity of these groups in one molecule. So when you think about polymers in solution, really polymer solvent interactions are crucial in lots of different areas of polymers. So this includes polymer processing, which is what my group focuses on, electrospinning, coatings, film preparations. But it's also important in things like polymer purification, such as after you synthesize the polymer or when you want to separate waste polymers, as growing as a research interest area. Then, of course, they're very important in formulating, mixing polymers with other materials. A lot of my group focuses on the formulation side as well. And then finally, self-assembly and the fancy ordered structures. So to understand these and be able to plan out processes and materials, we have to understand our polymer solvent interactions and understand our solubility behavior. So to start with, I want you to think about polymers in solution just on their own. So we're going to think about polymers as liquid, or polymer solutions as liquid solutions with these long macromolecular chains but small light molecules of solvent with them. So the size of a monomer in a polymer is about the same size as a solvent molecule, but the polymer molecule is very big. So you see this GIF here that's showing the movement of a large polymer molecule, and you can see it takes lots of different configurations and moves around as a flexible chain. And in this illustration, we see it being only one size, but depending on the environmental conditions that chain is in, it can take up much more space or much less space. So to put this in context, I want to talk about, or have you guys think about this with it, making a polymer molecule more macro size. So let's say we take a chain that has 10 to the 10 repeat units, so a pretty big polymer chain, but I'll assume all of our bond lengths are 1 centimeter. So much, much larger, of course, than a regular molecule. So we multiply all length scales by a factor of 10 to the 8. So if we have attractive interactions between monomers, so they really like each other, they tend to attract each other, that polymer will take up about the size of a classroom. If we have no interactions between monomers, so they kind of ignore each other, they don't repel or attract, then that polymer will take up space the size of a college campus. If they have short range repulsion, where there's some repulsion, but it's not strong, it'll take up the size of a city. And if you have long range repulsion, it'll go all the way, a quarter of the way to the moon. And so what I want to emphasize here is that polymers really span a huge space of length scale, and that the kind of distance they will extend in solution depends on their interactions with themselves as well as with the polymer. So put this back on a normal length scale, not these astronomical length scales. Our polymer conformation can span anywhere from about 100 nanometers to 1 meter. So if we have attractive interactions, we have a poor solvent, our polymer is going to condense and have a radius of around 100 nanometers for a polymer molecule. Then as we increase the quality of the solvent or make it more favorable to be dissolved, our radius is going to increase to maybe 100 millimeters. And if it's the very, very repulsive, so the polymer repels itself, then our radius could be 1 meter. And so it's kind of illustrated here where at 37 degrees, we have a polymer that's well extended. Or sorry, this one's 37 degrees. We've got a polymer that's crashed out. And then after you centrifuge it, you see that it actually doesn't take up a lot of space. But when it was soluble, it was more like the picture on the left side where you could pour it out and it was a fully liquid solution. And so as we think about polymer solubility, we really want to think about how this polymer transitions from this well-extended state into this collapsed state. And I'm going to try not to bore you too much with free energy of mixing, but it's really helpful to understand our phase diagrams. So when we think about our free energy of mixing, we have our delta G of mixing equals delta H of mixing minus T delta S of mixing. And a negative delta G of mixing is what leads to the spontaneous mixing, or it leads to this essentially being soluble. And so we've got these two factors, the enthalpy and the entropy of mixing, that play a role in whether this will actually spontaneously mix and be soluble. The entropy of mixing is this increase in uncertainty about the placement of molecules as they're mixed. And then the enthalpy contribution comes from breaking and forming of chemical bonds. Now, I put the bonds in quotes because they're more associations in this case. They're not covalent bonds, but it's essentially associations being ripped apart or put back together. So if we think about our, a simple system, say we have two solvents, our entropy of mixing is going to be uncertainty about whether they're placed, where they're shown here, or they're placed all mixed up. And then our enthalpy is going to have to do with how much the orange dots like each other versus how much the blue dots like each other. Now, when we think about how to work with this for polymers, the big difference between polymers and other systems is that polymers, the units are connected. And so each of these monomers, which are about the same size as our solvent, is going to be covalently bound to another one. And so you have one molecule that's very big compared to the other. And that leads to some differences in the mixing and the energy of mixing compared to, liquids and liquids or vapors and vapors. So I'm going to talk through each of these, the entropy side and the enthalpy side. So the entropy side, it depends on the volume fraction of each component, which makes sense whenever we think about any mixing. One of the key elements is how much of each component that you have. In this case, it's better to represent it as volume fraction. But it also depends on the size of the polymer molecules. And the way it does that is through the number of moles of each component. So the lowercase n is the number of moles of component 1 and 2. So if you have a polymer, you have very few moles of it compared to the moles of solvent, right? Moles have to do with the number of molecules. So if you see that image in the upper right side, there are 3 polymer molecules in that image, even though the volume fraction of the polymer is still somewhat reasonable. There's still only 3 molecules, but there's a lot more molecules of that the solvent, which are the white circles. And so what this means for mixing is that N2 is very small, and so your entropy is always going to be relatively small for mixing of polymers with a solvent or polymers with other polymers. The other thing to note is that entropy is always favorable towards mixing. So polymers always want to be mixing. Enthalpy, on the other hand, is our associations between components. So component 1 and the other component, another molecule, component 1, break when they mix, and then component 1 and 2 have to form when they mix. And in the Flory-Huggins free energy of mixing model, we define what's called an interaction parameter, chi. And chi captures these interactions. So it captures how much component 1 and 2 want to be associating with each other. And then the enthalpy also depends on the volume fraction of the polymer and the moles of solvent. So the reason I talked about this is I want you to be thinking about how these 2 elements play in. So for polymer solutions compared to other material types, the contribution from the entropy is actually quite small. Now it is negative, so it's going to drive it towards mixing, but it's going to be small because that polymer is that big, large molecule. So most mixing behavior depends on what's called the Flory-Huggins interaction parameter, or chi. And so if your chi is going to be positive and large, then you're not going to have mixing. And so how we think about this is we're going to tie it into the phase diagrams. So phase diagrams are showing our locations of having 1 phase versus 2 phase, where we plot our temperature on the y-axis and then some sort of composition on the x-axis. Now, frequently with polymers, we want volume fraction because that ties well to Flory-Huggins, but experimentally, weight fraction is easier, so that's also plotted. And the way you want to look at this is that in the 1 phase region, your polymer is going to be extended. So we talked about those different polymer conformations. Your polymer is going to be nice and extended in the 1 phase region. In the 2 phase region, you're going to have it collapsed. So it's precipitated, and you're going to have this full phase separation here. And so in this particular diagram, at higher temperatures, we have our 1 phase region, we have our phase boundary, and then we have our 2 phase region at the lower temperatures. So this particular behavior is what you might expect, given your experience with other molecules, is that as you heat something up, it goes from a 2 phase region to a 1 phase region, or it precipitates on cooling. This particular system is called an upper critical solution temperature. And so that's where you precipitate on cooling, and your binodal marks this UCST at various compositions. Now, polymers, again, being kind of unusual molecules, they can also go in the other direction. So polymers can precipitate on heating. They have what's called a lower critical solution temperature. So at low temperatures, you have 1 phase, and as you heat it up, it'll crash out, and you'll have 2 phases. So this is, sometimes a little bit hard to remember because it's not the most common behavior, but it actually is a really important and common phenomenon in polymers. And it ties to the free energy of mixing. So this is why I talked to you guys about the free energy of mixing at the start of this. So delta G of mixing, we want it to be negative if it's soluble or 1 phase. It'll be positive if it's 2 phases. And then our entropy of mixing is always negative. And then it's that enthalpy of mixing that drives things. So if the enthalpic component is big, it's going to override your entropic component, and you're never going to get mixing. But we know that our delta H depends on chi, this chi parameter. So if, as your temperature increases, then chi decreases, so if chi's dependence on temperature is inverse, then you're more likely to mix at high temperatures and you get this more typical behavior of the UCST. But what can happen is that as your temperature increases, your chi also increases. And then you're less likely to mix at high temperature and you get this LCST behavior. And this can happen due to specific interactions like hydrogen bonding or other types of kind of important molecular interactions. You can even have, I just want to show one example where you have a system with both an LCST and a UCST. So this is polystyrene and N-propyl acetate. It displays both of these behaviors. So you can see those in the figure there. And what you can also see is this dependence on the size of the polymer, more specifically, where that one phase region that's in between decreases as you increase the molar mass of your polymer. So now we've got some good solid basics on polymer phase diagrams. We want to think now about how to actually construct them and potentially use them. So we can use a Crystal16 to measure our cloud points or measure where we transition from low transmission to high transmission or vice versa, and construct the phase diagrams. So here I'm showing some data from polyvinyl peroxidone in acetonitrile. It has UCST behavior because you can see that where we start at a low transmission, low transmission. So we have a lot of particles in there at low temperatures. And as we heat it, it goes to a high transmission, or we're getting solubilization of the PVP. So from this data, we can see the fact that the PVP and acetonitrile system is a UCST system. And then we also see that as the concentration of PVP increases, this temperature of the phase transition increases. And so we can take that and plot our temperature versus concentration phase diagram. And you'll see I only had 3 data points here. And then I kind of, since we started at 10 degrees C, I couldn't go too far. But I sketched a curve at least. And so from this type of data, we can get these nice phase diagrams. Now, often for practical matters, we actually don't care about the full phase diagram. We might just want to know solubility or LCST versus UCST behavior at specific temperatures. So here, I'm showing us measuring the transmission versus temperature through 2 different temperature ramp cycles, where our high point temperature hold is at 60 degrees C and our low point temperature hold is at 10 degrees C. And we see that the transmission here decreases while we heat. So that red curve is the temperature set point. And as we heat it up, so like maybe at the very start, for example, then we see the transmission decreases. So that means in this case, which is polypropylene and toluene, we have LCST behavior. So the opposite behavior is the last example. So this type of data has a really nice practical tie to processing and formulations. It tells us if we expect our polymer to crash out on heating or on cooling. And it also tells us that in this case, our higher concentration one never gets or higher concentration ones never get as soluble as lower concentrations. So our 50 mg per mil is a gray curve. And even, at our lowest hold temperature of 10 degrees C, we still reach only a transmission percent of 30. So this gives us a lot of helpful data for designing our process and formulations. But how do we use this to do an even better job of improving our ability to formulate? So this is where I want to give an example of research we've done in our group with using the Crystal16 for polymer solubility. And the area where we're particularly interested in here is enabling machine learning models to help us predict our solubility without having to do all the experiments. So lately in the field of materials, there's been a growth in pairing robotics for high throughput data collection with data science to predict material properties and perform inverse design. So when it comes to the solubility side, we may want to be able to formulate a product. We may want to quickly remove a solvent that's been banned. So you'll see I've got DCM up there, which has been a headache for many of us. Or you may want to reformulate to try to increase your percent solids, but still have things be soluble. And so using things like machine learning and inverse design could potentially help us do that faster if we have good predictions of which solvents a polymer is soluble in. And the first step we have to do for this is to standardize the measurement parameters, because a lot of the existing data sets on polymer solubility are not standardized, and polymer solubility depends on a lot of factors. So that's what's shown in this fishbone diagram here, is all of the different, or many of the different solvent and polymer features that impact the measured solubility, but also even the measurement parameters, things like the temperature ramp rate, the hold temperature, mixing speed. These are going to impact the measured solubility of a polymer. And so the first step that we did was to design a standardized method so we could take all of our data in the same way. So we did 2 cycles. The reason we do 2 cycles for polymers is they're very, very sensitive to thermal history. And so the first cycle helps create a more uniform thermal history, and then we use the data from the second cycle. And then we set specific temperature ramp rates, hold temperatures, mixing speeds, and hold times. The details for how we selected those are in the paper referenced there by my student, Mona Amirhasari. Then we collected 1,055 data points, so 30 different polymers and 50 different solvents at multiple concentrations, the same type of data I showed you before. So we created this nice large data set where all the different experiments were taken at the same conditions. And then to do our machine learning model, we classified the solubility behavior. So we set everything above 85% transmission, classified as soluble. Everything below 10% transmission is insoluble. And in between, we called partially soluble. We wanted a little bit more differentiation, not just calling everything fully insoluble. And so from these classifications, we aim to train a machine learning model and have it then be able to predict for unknown species whether some polymer and solvent system are soluble, partially soluble, or insoluble. But part of our objective was also to see, do we need to use a Crystal16? Do we need to use turbidity measurements? Or can we just mix these up in a vial, look at them by eye, and train a machine learning model on that? So our question was, how does the performance of a classification model change when you have low fidelity data, such as visual inspection, versus high fidelity data? So we also collected a visual inspection data set. We have a lot of undergrad researchers at Georgia Tech, so we can manage to do things like this. We collected 1,455 data points, lots of different polymers and solvents again. These were all done at 5 mg per mil polymer in the solvent, and they were inspected by a lab member after 24 hours and classified as insoluble, partially soluble, or soluble. Then we did our machine learning model. So I'm not going to go into detail, although I'm happy to answer questions later. But we use a model XGBoost, and we use Morgan fingerprinting for the solvent and 1-hot encoding for the polymer. And we predicted how well each of these, the models trained on each of these data sets actually were able to do predictions. And so the visual inspection is shown on the left, and the transmission or turbidity data collected from the Crystal16 is shown on the right. And what you need to know about confusion matrices is that a better prediction is going to be darker color on the diagonal and lighter color in the corners. And so you can see very clearly that the predictions are better with the turbidity data than with our visual inspection data. And I specifically want to highlight this category because this really shows why it was so much better. So our visual inspection data set contains very few of the partially soluble cases. So it's the green ones in that bar with the hash lines, because it's really hard for your eye to differentiate partially soluble from either soluble or insoluble. But from our turbidity data, because we have specific quantitative values, we can much more readily classify partially soluble and separate it from the other classes. And so we had a lot more partially soluble data, which then leads to better predictions. So from this example of some of the research we've done in our group, we show that we can use a machine learning model trained on our data to predict the solubility classification, and then use a high fidelity experimental data set to improve the model performance. We think that this helps us, at least if nothing else when we write grants, helps us justify additional effort and cost to create these high fidelity data sets and improve our ability to predict polymer solubility. So with the last bit of time I have, I want to briefly talk about polymer precipitation, because I think it's a really exciting area to move into where there's not a lot understood at this time, and then how we use the Crystal16 for precipitation times. So the rate of precipitation is really important for the success of the process or even the properties of the product. So when you think about process design, the rate at which polymers dissolve and precipitate can set the throughput of solution precipitation processes such as recycling, some of these new chemical recycling methods, but also other processes. Because polymers are large molecules, they can actually have very, very slow kinetics. So even if it's thermodynamically favorable to dissolve, it can still take a very long time because these large molecules have to disentangle themselves and separate. On the property side, one example I have from my own research way back in my early days is the surface area of amorphous drug and polymer mixtures and particles that are made from those mixtures depends on the precipitation rate that you have. And the surface area then impacts your drug dissolution processes. So it's really important not just to know whether something's soluble, but how fast it's going to be dissolving or precipitating. And we chose for now to really focus on the precipitation side, but are thinking towards the future, towards the dissolution side as well. So precipitation in polymers is not overly well understood. What they think happens generally is they've got what's called a coil to globule transition. So this goes back to what I was telling you about these kind of polymer conformations, where when it's in a good solvent, it's nice and extended, and then it transitions into this collapse phase. So that has its own rate associated with it, and that is thought to happen first. And then those globules will nucleate and start phase separating and then grow as the process proceeds. So each of these kind of is its own rate process. But while thermodynamic theories have been developed for them, much is still poorly understood. So really digging at the true kinetics of these processes, one of the big areas of weakness is that most of the theories in this have been done for systems with low concentrations, where a single molecule can collapse into that globule first without hitting another molecule. But a lot of industrially relevant formulations are not going to have such low concentrations. And then finally, there's a lot lacking in understanding the specific features of the polymer and solvent and how they impact the kinetics. So what's nice with the turbidity data that we've been working with is that we've been able to collect some kinetic parameters. So this first set of kinetics we're looking at is really showing how we can see the transitions occurring. So in this case, as we cool down our system, we see precipitation of the polymer. And we think generally that first range, which is the hatch zone, is kind of that nucleation and phase separation phase, where it's kind of like an induction time in other materials. And then the growth is the rest of that highlighted in blue. And so from the Crystal16 data, we can capture some of this behavior, which we're hoping will help us understand what's going on. But we also want to be a little bit more quantitative, right? We're engineers, we want quantitative information. And so one of the areas we're looking at is using something called the Avrami model to describe the polymer precipitation. So this describes the phase transformation rates when they follow an S-shaped profile, as seen on that figure there. You have initial slow phase, which we think people think is the time required for nuclei of the new phase to form and begin growing. The intermediate phase is the nuclei growing into particles, so those globules growing further and further in size into particles. And then this late slow phase is where there's very little material left to transform to the new phase, so you don't have a lot of growth. The Avrami model is shown here. I'm not going to go into the details, but there's kind of three main parameters that we want to pay attention to. The first is a different chi than the chi we use, talked about earlier, but it's a fraction of material that's transformed at time t. We have k, which is a growth rate parameter, and then that exponent n, which provides some information about the type of nucleation and growth mechanism. Now, when we think about polymers, the Avrami model is somewhat limited, partly just also based on the experiments we do. It only applies to isothermal conditions as opposed to things on a ramp, so it can be slower to measure. It also only considers primary nucleation, which can be a problem, as anyone who's worked with crystallization knows, does not happen that way most of the time. And then when it comes to polymers, one of the weaknesses is that it relies on assumptions such as a constant growth rate and random distribution of nuclei, which is not necessarily true for these large molecules like polymers that tend to stick to each other easily. But despite these weaknesses, we hypothesize that we can use this Avrami method to understand and compare precipitation data from turbidity data. So just a very brief example of this. So we're measuring our transmission versus time. We can do this during a temperature ramp or during an isothermal hold. And this is another set of data where you can see the temperature ramp in red and the transmission in black. And what we've done is we've defined two metrics just from this data that are simple metrics. One is the induction time, so that time to the first decrease in turbidity. We're not sure if induction is quite the right phenomena that you have in polymers. It may be more of a combination of our coil to globule transition plus induction of the phase separation. And then what we're calling delta T, for lack of more creative ways to call things, is that time to the plateau turbidity value, which that should capture the growth phase as well. Then we have our Avrami equation, which we've adapted to use with turbidity data. So we base this on percent transmission as a parameter that shows how far our phase separation has proceeded. And we show that we can actually fit this Avrami equation very well to some of our data. So we have polyethylene glycol and NMP with this Avrami fit so the experimental data is in blue, the Avrami fit is in orange. And I just highlighted a couple of the fit parameters that are important. Our rate constant, 3 × 10⁻⁵, and then our Avrami exponent of about 3, which makes sense because that's about what it should be for a 3D type of nucleation mechanism. We also see that it works well for polyethylene glycol and ethyl acetate. And in this case, we've shown it for a couple of different concentrations, going from low to high concentration, so that from this, we can extract actual rate data. And that's what I'm showing here. So I have our concentration, 3 different concentrations, and showing how our growth rate increases as our concentration increases. So this is consistent with what you might expect for a precipitation process. As you have more polymers in there, you're going to have a faster growth rate. And so we think that this approach of using this Crystal16 rich data set, we can analyze both the induction time and delta T, but also tie it to specific theories like the Avrami equation. So to summarize, polymer solutions are described well by thermodynamics of mixing. And what I wanted to kind of get across in this to people who may not be as familiar with polymers is that they display both LCST and UCST behavior depending on this chi parameter. The Crystal16 enables collection of these large turbidity data sets that can be used to train machine learning models. And we showed specifically that our predictions are improved with the turbidity data sets compared to visual inspection. We also showed that I also discussed how polymer precipitation kinetics are important, but tend to be poorly understood. And they're thought to follow 3 stages: our coil to globule transition, nucleation, phase separation, as well as growth. And that the data from the Crystal16 can be fit to the Avrami model and extract some additional kinetic parameters. So with that, I want to thank the people who've done this work. So most of this was led by Mona Amrhasari, a PhD student from my group, and with collaborators on the computational side, Joe Kern, Rampi Ramprasad, Fani Bukovala, and Jacob Sweet. And these are just some of the undergrads that have worked on this. There were more in the early days as well, but lots of helpful undergrad researchers. And the work was funded by the Office of Naval Research. With that, I'm happy to take questions.
Thank you very much, Blair. Highly appreciated that you have shared this data, and also a bit the background on polymers. To be sincere, I do not know that much about polymers and so, but it was really useful also to learn about LCST and UCST. Sometimes we get these questions from our customers. Indeed, mostly customers that they are in other industries than pharma, not that much in pharma. Really useful. And to be sincere, I was also looking when you did the comparison with the eye and then with the Crystal16. I was like holding my breath. I was like, what are we going to find out here?
Yep.
But nice to see that actually, indeed, from the transmissivity, really qualitative data you can get out to feed into the models and so. And at the end of the day, I think you always need some experimental data to to validate in a way models and so. And I guess also this model, my question related to the model in general is that because you had quite a large number of conditions there, also polymers and solvents and so on. Do you expect that if, as an industrial, let's say in industry, I start now, I just put inside into the model my data that I get from the polymer that I want to look at, and you get something out, or do you expect that you need to fine-tune further the model, or how easy it is? When I look at the amount of data, thousands, and so I think there were many more experiments than
Yes.
those.
Yeah, the idea is that we build a model that people can use to predict and narrow down their composition space for their future stuff. I think everyone building their own model is probably not what people want to do, because it does take, as we showed, quite a bit of data. There are also commercial companies that are doing these types of predictions as well, where just software can be bought. But the idea is to create these models that people can use to narrow the parameter space for experimentation so that they don't have to do a lot of them. And then if you do have, say one polymer that's super crucial to your particular, I guess, application area, there are other approaches that look more like with this. So we focused on lots of polymers and lots of solvents to diversify the chemical space. But you could also do one polymer and solvent and really focus on lots of different concentrations, lots of different crystallinities and other input parameters. So there are researchers doing that as well. And then they can maybe more accurately predict not just soluble versus insoluble, but is it going to be soluble at 20 mg per ml?
Yeah.
Or 30, right? So ours is a little more limited on that side because we focused on chemical diversity, but there are people kind of focused on other elements of it.
Are you planning to make it as a commercial thing? Because I think it should. I do see a business model in it, Blair.
Yes. Yeah. So no. This is not quite the commercial thing I would want to do. But Rampi Ramprasad has started a company. So he doesn't use our data. He uses more literature data. But he has started a company called Mapmerize, where they do solubility predictions as well as other material property predictions. There's another company I met with recently called Citrine that has commercialized software for material property predictions. It's a little more formulation focused than Rampi. So there are people doing it, not necessarily with our type of data. And I think, our type of data is nice because it is this higher quality than literature data. But that means, of course, people have to invest in making it.
Yeah, this is really one big step forward, because I remember many years back, I think more than 20 years back, when we were doing in the lab amorphous solid dispersion. So to try to increase the solubility of a drug poorly soluble drug and dissolution, actually.
Mm-hmm.
So we had these big databases of multiple polymers that we had to try here in different concentrations, different volumes, and so with the API, also the APIs in
Yep.
different drug loads and so on. But of course, everything was taking us back to solubility. What is the solubility? In the multiple solvents also, you have a
Yep.
big list of solvents. Of each of one of those polymers in the different solvents at the different temperatures, because then you had to have that to be able to design your experiments. How am I going to mix them, and how are we, and also
Yep.
then afterwards, after you get some results, how do you associate it? So such a model definitely.
Yep. Yeah, and the multiple solvent case is what Jacob Sweet, who's listed on this, he's taken over doing some of the work on that. So we're moving forward in mixed solvents as well. It's a little bit more complicated because we don't want to take thousands of data points of mixed solvents. But yeah, we're definitely working on that case too, because I think industrially that's actually the most relevant. That's what we get from every industry I talk to is like, okay, now what about mixed solvents?
Yes, indeed. Yeah. I have a few questions I'm going to write to you besides some congratulations on the presentation. One of the questions, using the Crystal16, how fast and accurately can you construct the binodal and spinodal curves on an API polymer solvent ternary phase diagram? Are there available publications that compare results with PC-SAFT predictions?
That's a good question. So we purposefully chose not to construct the full phase diagrams in the interest of having larger chemical diversity. But each of our runs is, about, let me go check actually. There it is. So yeah, it's about 14 hours. And again, with polymers, it's good to use data only on the second heating. So you will want to, or second cooling on the second cycle. So you still will want to have them about that long. And then to do the phase diagrams, I think people often get decent data with maybe 10 different concentrations if you're starting in a good spot. So it's doable if you're not trying to get a large diversity of polymer solvents. But if you basically take each of our data points and have to do 10 of them, that would get prohibitive on time. But I don't know. I haven't looked at people doing it with the polymer and drug together. I would have to, if you want to, whoever asked that question, if you want to email me, I'd be happy to look into it a little bit.
Oh yeah, this is something that I don't remember if I said it in the beginning. Would you share your email address with everybody so that if they have a question, they contact you directly? Is it okay for you, Blair?
Yeah, that's fine. I should have put it on the slide. I forgot. But I'm also very easy to Google. Georgia Tech. I'm the only Blair Brevin. So
okay, perfect.
My email address is available there. So yeah, I'm happy if you guys reach out.
And if needed, we can also share then your email with them. Another question, Professor Bregman. I have a question about your study on the term partially soluble. In polymer solubility, if 10 milligrams of a homogeneous polymer is placed in a solvent, it should either remain undissolved, swell, plasticize, disperse, or fully dissolve. Thermodynamically, it cannot be half dissolved and half undissolved at equilibrium. Okay, we go into thermodynamics now. When fully dissolved, all chains enter solution. Could you clarify what partial solubility means here?
Yeah, so that's a good point. We are using partial solubility to represent kind of things that fall in intermediate transmissions, where the goal is more on the practical side than on the thermodynamic side, so that if someone finds a polymer solvent system that's classified as partially soluble, they know shifting your temperature, shifting your concentration a little bit is likely to push it into our fully fully soluble or fully insoluble range. So it's true, it is not a good rigorous thermodynamic description. It was more of a way to help create a little more granularity to help formulators know which direction to move in.
We have somebody here writing potentially, I guess, for a collaboration with you, Blair, for wildlife side water ponds or something like this. But we will share afterwards all the details. So, but we will share the details with Blair, and then I leave it up to you to communicate there if there is an interest. And one more question, because I also look at the time. Very great talk. In pharma, we use polymer for amorphous solid dispersion formulation. What is a suitable way to find out the interaction between API and polymers?
Oh, that's a difficult one.
Polymer for formulation development.
Yeah, the experimental, so the concepts I talked about with Chi and free energies of mixing all translate very well as well to the solid phase solubility of amorphous drug in the polymer. But measurements of Chi and measurements of solubility parameters are very difficult. I don't know that I have come across any easy way to do that. I think there are some people looking at computational ways to predict them. So when we do these machine learning systems, we do what's called fingerprinting of our polymer and our solvent. So we look at 50 to 100 different features of the molecule, and the machine actually learns how those features tie to the solubility, not just the name of the polymer, the name of the solvent. Yeah. And so even if we can't have data on the drug and the API and the polymer, learning on features based on other systems such as ours might be able to push you in the right direction. And I think some of those approaches, as well as some based on simulations, are being used. But it's in the solid phase, it's definitely very difficult to measure whether things are soluble or not.
Yeah, and I think well, there's a lot behind it. Now I was thinking back what I used to do, but it also depends on what type of formulation. And
yeah, I say my PhD, I did solid state NMR to do this, but I do not recommend doing a huge variety of solid state NMR to get solubility parameters.
Yes.
But it does work. You can learn about it. So that's what I did in my PhD, but it's very hard to do that at scale.
Yeah. I think this is it. Looking at the time, we have to close here. As I said, we will also share the email address of Blair, so you can also contact her directly. We will also share with you everything afterwards. Tomorrow or the day after tomorrow, all the attendees and also the ones that they register but didn't manage to attend today, they will receive an email where they can rewatch the recording and also download the slides. Usually on our website you have all this, it's a big database and you find everything back. Blair, thank you very much. Deeply thankful to bring this topic to our customers and to our attendees today. I can only say that I look forward to a next webinar with you. I learned a lot, and I am sure that you still have a lot of data from Mona's and the other students. Once again, thank you very much. Thank you all for being present, attending today this webinar. And end of November, we have a next webinar session scheduled. Thank you all. Have a good afternoon or good evening. Bye.
Bye. Thank you.